Hi, I'm Soroush. I'm your TA. You probably know me. And in this session, I will talk about Lightning Network. You may have some ideas, and I try to explain the main novelty in this work, which originally published in 2016. And please interrupt me whenever you have a question, and we can begin. Okay, so why do we need uh, a Lightning Network or a concept like uh, off-chain solutions, or sometimes we call them layer 2 solutions? It's because a blockchain has scalability issues. So we have four main problems. The first and the most important is throughput. Bitcoin has something like 3 transactions per second. Ethereum has 14 transactions per second. And when you compare these decentralized coins to a service that we use daily, like Visa or PayPal, you see that blockchains, they are really, really slow. So we need to scale it, right, if we want to compete. The second problem is latency, right? Whenever you pay something with Visa or I guess Alipay or WeChat, you get an almost instant confirmation. But for latency, as you know, whenever you submit a transaction, first you need to wait for next block, and then you need to wait for some confirmation number. For example, a common sense in the community is that for Bitcoin, we need to wait 6 blocks. So each block in Bitcoin, the duration is 10 minutes roughly, and 6 block, it's 1 hour. And of course, if you imagine, let's say you go to a Starbucks and you want to buy a coffee, you don't want to pay for an hour, so you can get your coffee. The next scalability problem is cost. And of course, so we are used to, if we don't, I'm not sure about the bank policies here, but at least from the things that I've seen, right, whenever I transfer or FPS money to someone, I don't need to pay transaction fee. But in blockchains, you have to pay. So these numbers, they're a little bit old, but you can see, right, even everything compared to zero is too much, right? For Bitcoin transaction, $66, or for Ethereum, roughly $1, which we don't like. If we can do it cheaper, it would be a lot better. So, and the last scalability issues is the storage, right? But in Ethereum, we always says that, okay, everyone can be a node in the network, but in reality and practice, you have to have a good resources to run a node for a blockchain, for example, Bitcoin or Ethereum. Here it says that this is just a storage, right? But you can imagine, right? You have to have enough even computation resources, right? Even to verify some transactions. So here for Bitcoin is half terabyte, and for Ethereum is 2 terabyte. And you should know that this 2 terabyte it's for light node, and in the light node you cannot you don't have access to historical information. For example, you just know what is happening exactly right now. If you want to find an origin of transaction, I don't know, in 3 days ago, you cannot do it. And if you want to run a full node, you have to have 12 terabyte, which is quite a lot, right? You cannot do it on your phone. And honestly, you cannot probably you cannot run Ethereum either on your laptop, because you have to probably that even today's laptop, they don't have enough computation resources to have a full node, or it will be really, really slow. So we want to scale blockchain to fix these 4 problems. And usually in in the community, we have three main approach to scale a blockchain up, right? And these ideas, all of them, they are, you can categorize all of these solution as an off-chain solution. And what do we mean by off-chain solution? Is that we don't need to execute or follow the whole protocol, all of them on chain, right? We can resolve or argue some of it without posting anything on chain. So you should know, every time I post a transaction to blockchain, or here I call it on chain, I have to pay. I have to pay a transaction fee and I have to wait. But if somehow I could have some start state and update this state without using blockchain, right? Or in this area, we call these computations off-chain computation. If I can update the state in off-chain computation, and then at the end I just publish the final state, then I will save a lot of money, right? Or I can do computation faster, right? But this is nice. The general concept, it's kind of good, but the whole idea that we use blockchain or any decentralized ledger, because we don't want to put our trust on a third party, right? So no matter what we do here, we should not stay away from our main principles, right? We don't want to use any centralized database or any centralized authority. So I don't want to trust anyone. So if I want to move some of my computation from a blockchain uh, to from on-chain to off-chain, I should always be careful that I should do it without putting trust on any third party. And there are three main approaches to move computation from on-chain to off-chain. And these approaches are state channels, rollups, and sidechains. In this session, I will focus on state channels, which we talked about Lightning Network, but to give you some sort of idea how other two work. Rollups, there are like, I have two blockchain. So it seems like I have one main blockchain. And then I have a secondary blockchain, which publish blocks a lot faster. And every other time, I put a checkpoint to the main blockchain. We call this idea rollups. Sidechain, it's something similar. And again, if you're interested to read more about rollups, you should search optimistic rollups or zero knowledge rollups. They give you a very good idea how this protocol works. But in this session, we put our focus on state channels, and we will talk about Lightning Network. Any question so far? Okay. Oh, okay. So it is similar to having rollups. Yes, it is similar to synchronizing every M block. And usually these protocols they have their own rules, right? You will go and read their rules. For example, the two famous one is either, I believe the name is Polygon. It is on Ethereum. And even sometimes they are not decentralized. They're like, there's a guy says you should trust me, but I do everything faster and I have a good history. And every other block I put a checkpoint so you can check on the main chain. So sometimes they are not these layer 2 blockchains, they are not even decentralized. But the main idea is, you're right. The main idea is we synchronize every M block. Okay. So let's move on with our Lightning Network. Lightning Network original paper was around 2016. The idea, people were interested in the idea because they could scale Bitcoin without changing anything. So they built their protocol on top of the Bitcoin. Or in their words, they like to say that we use Bitcoin smarter than others. But no matter what, their idea was kind of new. And there's a book, and you can read the paper. And here I will discuss the main idea. So here, our main idea is something like this. So let's say I have Alice and I have Bob. And they want, and because they know each other, they want to pay each other frequently, right? And they don't want to, every time they want to pay each other, they don't want to put or publish a transaction on Bitcoin. And they have a roughly idea, and they say, okay, let's say we have a channel and this channel has a balance. And let's say the capacity of the channel is between two participants. The capacity of channel is 1 Bitcoin. And at first, both of them, they have half of Bitcoin. And now let's say Alice wants to pay Bob 0.1 Bitcoin. What do? They just update these balances, right? So the Alice balance will be 0.4 and the Bob's balance will be 0.6. And now let's say Bob wants to pay Alice. So let's say Bob wants to pay Alice 0.3 Bitcoin. So the Alice balance will be 0.7 and the Bob's balance will be 3. So this is kind of nice, right? And they can pay each other very fast. But again, we have this very naive idea, but first we want to implement this idea with what we have in Bitcoin. As you know, in Bitcoin you don't have a very rich script language, right? What we can do is very, very limited. And also, even now they want to pay each other a lot, they still don't trust each other. So they want to implement this idea without trusting each other or without putting their trust in a third party. If they want to do the same thing with Bitcoin, for each transaction, they have to create, for each transfer, they have to create a new transaction. But they don't want to do this, right? We want to do it faster. What we do here, we use, first, we use the idea of 2-of-2 multi-signature, which I believe Amir have talked about in the course. And based on this, we will build this protocol. And so every time they bind to each other, they negotiate a new distribution, right? And at the end, if they put the final distribution, right, at Bitcoin, then they have reduced their cost. or as I said here in this picture, if let's say if they put the first transaction on chain and here the balances, sorry, here the balances are half and half, and then they update the balances here. Here it will be 4, 6, here it will be 3, 7, and if at the end they put, I don't know, if here the last transfer, the balance is 0.1 and 0.9. And if they publish this on chain, then they have managed to do a lot of transactions with just two, and a starting transaction and the final transaction. So, and because these middle transactions, we don't need to publish them, so they are fast, they are cheap, and I can do as much as I want, as long as I can trust. I can trust the protocol. So let's see how we can do this. Now we want to create a channel between Alice and Bob so they can update their balances. And let's check some very basic concepts. You know that the Bitcoin transactions, they have some outputs and they have some inputs, right? So inputs, they are come from previous transactions, and outputs, they are actually, when you say you own some Bitcoin, you know the private key to these outputs. And so, and we want to, so this is the basic Bitcoin transaction, which hopefully you guys, you know about. And again, to recheck everything, and you know, I cannot double spend. So every output you can only spend it once. So let's create our channel. To create our channel, first we need to fund it, right? As I said, each channel, they have capacity. And so, and let's say, here. So let's say Alice, she wants to create a channel to Bob. So I have Alice and she wants to create a channel with Bob. And she wants to put all the funding. So at the beginning of the channel, all of the funds would be on the Alice side. So she wants to create a channel with 140,000 Satoshi and to Bob. So I said in Lightning Network, in the transactions, we use the idea of two multisig. So we have a channel, and every time we want to update our balance, both participants, they have to agree. So that's why we need both signatures to update a channel's fund. So here, Alice has a transaction. The input is 2,000 K, and she doesn't want to put everything on the channel. So here, she puts 60,000 to her wallet again, and this will be the fund transaction for our channel. So this means that my channel now can continue, right? Now I have an output that I can update it. And right now you have a very good idea that, so we want to update this funding transaction every time. But here I have a problem. Let's say Alice puts Bob's address to the first output, to the 2 of 2 multisig output. Then, as long as Bob does not sign this output, Alice cannot get her money back. Or in another word, Bob can take Alice's money, or can take it hostage, right? He can prevent Alice to get her money. So before Alice create this transaction, she needs some sort of guarantee, right? That Bob cannot do this. The first novel idea in Lightning Network is that you can sign, you can have a transaction, right, without having the parent. So the idea is something like this. So if this is an Alice transaction, right, here I have two output. If Alice has a valid transaction here, that she can spend this output, right, and she has Bob's signature, then she has a guarantee, right, that Bob cannot steal her money. And the first novelty here that Bob can sign this transaction without having the parent transaction. Without Bob can sign the child transaction without knowing the parent transaction. Alice can create the transaction. Alice will generate the transaction hash and put transaction hash here and give this child to Bob. If Bob refuses to sign this transaction, then Alice will not deploy the original transaction or the parent transaction, right? But if Bob signed the transaction and give it to Alice, then Alice, she's sure that Bob cannot take her money, or Bob cannot prevent her to spend her money. So here, when we have a funding transaction, before anything starts, Alice creates a refund transaction and will give it to Bob and ask Bob, hey, can you sign this? And if Bob refuses to sign this transaction, then she will not start a channel with Bob. But if Bob signed this transaction and give it to Alice, then she can, she has a guarantee, right? She can deploy this transaction to Bitcoin and keep this transaction for herself. So again, the first novel idea here is that if you want a guarantee from someone that they cannot take your money hostage, you can always ask them to first sign the refund transaction. Okay, and so Alice will fund a channel and then ask Bob to sign the refund transaction. So she always has some sort of guarantee that she can get her money back. And now this is the first idea. And now let's discuss about the second idea about punishing dishonest participant. So now let's say I have a funding transaction, right? And this transaction, let's say I have a funding transaction here, and it has an output, right? And let's say at this moment, the output is half and half for Alice and Bob. So the current state of the channel, right? Let me put this here. And this is the output, and let's say it has 1 Bitcoin, and it's true of 2. So you need both Alice and Bob signature to spend this output. We call this funding transaction. And now let's say I want to update my channel. What should I do? So this is Alice, and this is Bob. And at first, the balance distribution is half and half. So I should have another transaction to spend the funding transaction. I call these transactions commitment transaction. This transaction has one input, which is this input, and has two outputs. The first output belongs to Alice, the second output belongs to Bob. And each output has half Bitcoin. And now let's say Alice wants to pay Bob 0.1 Bitcoin. So they should create, first they should say this transaction is valid. They should create another commitment transaction, which again, the input is the funding transaction and the outputs will be it will have two outputs, Alice's and Bob. And Alice will be 0.4 and Bob will be 0.6. So you get the idea, right? I have a funding transaction, and every month I want to update my channel. I will create a new commitment transaction. So to get a better example, this is my funding transaction. This is my commitment transaction. And in this commitment transaction, Alice has half a Bitcoin, Bob has a half of Bitcoin. And to get their Bitcoins, they don't need other one signature, right? So, but to spend this funding transaction, they need both signatures. So for the commitment transaction to be valid, they need both signatures. But if Alice wants to get her money or redeem her half Bitcoin from this commitment transaction, she doesn't need Bob transaction anymore. And now let's say we want to update this, as I said. So this is the state 0, and this is the state 1. Here we update this commitment transaction. And in the new commitment transaction, Alice has 0.4 and Bob has 0.6. And they updated the balance. And you need to know that, right? Whenever I update my commitment transactions, I don't need to immediately publish it to blockchain, to the Bitcoin. So the funding transaction is in the Bitcoin, which was our original state or beginning state. But for these commitment transactions, for example, Bob now he has more money. He doesn't need to update this commitment transaction or deploy it directly to Bitcoin. Why? Because Bitcoin transactions, they are like a real world check, right? Whenever I sign a check and give it to you, the money right now is yours, but you have, let's say, a month or something like that to go a bank and cash your check. And Bitcoin transactions, they are like this, right? If this transaction is valid, right, then actually Bob has 0.6 Bitcoin, even if the commitment transaction is not in the Bitcoin. That's how these Lightning Network or these payment channels, they are really fast. So every time I update this commitment transaction, I don't need to deploy it, right? So they can update this commitment transaction so many times without publishing it to the Bitcoin. And now I don't need to pay transaction fee. I don't need to wait for new block, nothing. The only limitment is the network capacity, which usually really, really, really fast. So this is really nice, right? Now I have an idea. But here the problem is, let's say Alice pay Bob, right? 0.5 Bitcoin. But nothing prevents Alice to deploy the original transaction, right? Because they are spending the same output in the funding transaction. If both of them got deployed, only one of them will get to the chain, right? Because you cannot double spend. You cannot spend an output in a transaction twice. So here I have a problem, right? So I need to give Bob some sort of guarantee that Alice can never publish the previous state or the previous transaction. And that's how usually these payment channels, or generally if you see other places, state channels work, right? We update our state and we give some sort of guarantee that the players, they can never publish previous transactions. Or if they do it, they will get punished. So now I want to give Bob guarantee that Alice can never publish the previous commitment transaction. How I do it? The first thing I need to solve, I need to somehow differentiate between Bob's and Alice transactions, right? Because I want to know who should I punish, right? Here I said that you should not. So Alice, she has a really she wants to publish uh, previous essay, and I need to know, right? Alice did it, Bob didn't do it. So I know who can I punish. So what they do in the Lightning Network, they create for the same channel state, they create two commitment transaction. They are almost similar to each other, but they have a very small difference, right? You can see these commitments, 1A and 1B outputs, they are the same, right? But if this transaction get published, the blue one, we know that Bob published his commitment transaction. So if something malicious is happening, Bob should get punished, right? Because he initiated it. Or in our case, if Alice published a commitment 1A, we know that Alice did it. So if something malicious is happening, Bob should be able to punish Alice. So this is good. And okay, now we know who we should blame, but we still need a mechanism so we can publish, so we can punish the dishonest user. What they do in Lightning Network, they give the other parties some time to punish the previous uh, to punish the dishonest user. So now let's say we are still on our state 0. So each one, they have half of Bitcoin, half and half. But now let's focus to Alice's transaction here. So if Alice publish her commitment transaction here, so we know that Bob should get her half of money immediately, right? Because Alice can never get that money anyway, right? This second output needs Bob's signature. But if Alice wants to get her money back, her half of Bitcoin, he should wait a little. She should wait a little bit, right? Here she should wait 1,000 blocks. So if she did something malicious, Bob has a time to punish Alice. What they do, uh, here it explains on the other side. So if Bob publish his commitment transaction, Alice should get her money immediately. And now let's say we want to update our state channel, right? So these two transactions, they belongs to previous states. And now we have two commitment transaction. And you should know, right? Every update, we have two commitment transaction for each side. So this is the blue ones. They are the purple ones. They are Alice's transactions. And the purple blue ones, they are Bob's transactions. So we create new commitment transaction with the same logic. But here it says that because Alice pays 0.1 Bitcoin to Bob, here we updated the balances. And again, these commitment transactions, they have the revokes and the delivery transactions. And after we update the commitment transactions, each player, they should create, or they should allow the other player to punish them, right? So here, these are old estates, and here, these are new estates. After we created new estates, Alice create a transaction, and here we call it breach remedy transaction. And we'll give it to Bob, and we'll tell Bob that, okay, you can use this transaction, which belongs to previous estate. So if I ever publish the previous estate, you can always punish me immediately. So now we know players, they can never publish an old estate. So because if you publish it, the other player can punish you. Or if I want to sum up what I explained, it works like this, right? We update our channel estate and we give the other players, or each player, Alice will give Bob a transaction, whichever Alice publish a previous estate, Bob can punish it. So in this way, Bob, now he has a guarantee that Alice will never publish previous estates, because if publish it, then Alice will lose all of her money, right? Because this transaction, if Alice publish a previous transaction, this one, Bob can get her money, but Alice needs to wait 1,000 blocks. And while Alice waiting, because Bob has a punishing transaction, Bob can get Alice's money. So Alice will never publish an old estate. Any question so far? Okay. So this is really nice. Now we have a very secure bidirectional channel between two players, and they can update or they can pay each other in these channels without publishing anything on Bitcoin. So they are fast and very cheap. And now we can use these payment channels to build a network. So here, let's say Alice, she has a channel to Bob, and Bob has a channel to Chan, and Chan has a channel to Dino. And Alice wants to pay Dino, right? But she doesn't want to create channel with Dino because she needs to put some liquidity, and she needs to put deposit. So she doesn't want to do it because it is expensive. What she wants to do, she wants to route her payments to Dino. And if we can do this, then we have a very big network graph, which everyone can pay each other without hosting any transaction on Bitcoin, which will be really fast. And so we need three properties if we want to forward payments. They need to be trustless. Again, I should not trust anyone in my payment rules. They need to be atomic. So either a payment go through completely or will fail. And I should be able to use multiple intermediate nodes. And how they can solve this? Because now each channel, they have their balances, right? So, so instead of Alice paying Dina directly, Dina will give an invoice to Alice, and they will create the same exact commitment transactions, but now they will use the idea that you guys already use it in your homeworks. They will use HTLCs, hash time like contracts. And basically, so Dina will give a hash of pre-image to Alice, and Alice and Bob. Alice will tell Bob, okay, I will give you this money, and you can get this money if you know this image. Bob will do the same thing with Chan, and Chan will do the same thing with Dino. And then Dino gets her money by claiming this image. And now Chan knows the image. Chan can get her money from Bob, and now Bob knows the image and can get her money from Alice. So this idea is very similar to the homework that you used atomic swaps. And now here it's really nice, right? I can use these very simple ideas that I have so far. First signing the children, and then HTLCs, and the top contracts can lock money until a block. So, and now I can forward the payment, right? And now this is really good, right? If Alice, if I just have one channel to Lightning Network, then I can pay anyone that I want, right? And they will be really fast. And in the in in the Lightning Network, like any other peer-to-peer protocol, P2P, we should have some sort of gossip channels or gossip protocol so people can introduce new channels or update the network. Hey guys, our channel now they are closed. So and basically they have three main updates that they want to tell the network, which like any other P2P network. And the three new messages, they are node announcement, which telling that, okay, I'm a node, I'm in the network, channel announcement, and channel updates, which you either close them or you increase the capacity. And now let's talk about the next important idea in the Lightning Network. Oh, sorry. As the channel capacity is limited, proportional to TX amount. No, they are a lot cheaper, right? Because my time is a little bit limited. But here to incentivize Bobs and Chan to forward my money, I will pay them some sort of fee, right? That which they get by the difference. But these fees, they are a lot cheaper compared to Bitcoin transactions, because if they are not cheaper, then I will go and use Bitcoin. And basically, basically they are not proportional to what you pay in the Bitcoin, in the real Bitcoin transactions. Okay. Okay. Yes. So let's move on to our next problem. Our next problem is pass finding our payment delivery, right? As I said, so we have a graph of channels. If I want to pay someone, I need to find a pass and find some peoples or some hubs that they are willing to forward my payment. And so this is a problem which is currently people they are researching about if you're interested. And if in this example, if you can see, I have a network and each channel, they have different capacity, right? So if I want to forward a large payment, I cannot use any channel, right? They should have enough capacity. Or uh, and also you should know that the balances they are not announces. They don't announce balances in the network, right? Here that I know I have 2 million Satoshi in this channel, but I don't know the distribution. I don't know it's either 1 million or 1 million or half million or 1.5 million. And actually, this is one of the advantages of Lightning Network that people's this is the privacy part, right? You cannot follow the money or you cannot see who will pay who, right? Because we don't because the participants they don't announce balance distributions. And now you can get it right. If S want to pay R, either first he needs to find a proper way, and then he still doesn't know, right, if he can use this pass or not, because they might not have enough balance on that side of channel, so they cannot forward the money. And I have other criteria find to find a path in my network. So as I said, uh, each hub, if they want to forward your money, they will request a fee from you, right? And they have a different methods to do this. For example, here the base fee is 100 and the fee rate, which is based on the amount of your paying, it's 100. So whenever I want to find a pass, I should know uh, I should have a strategy or algorithm to so I can do it faster and cheaper. And also you should know some points here. First, of course, the small payments they have a better chance to go through, right? Because because compared to the network capacity, right? You have more chance that that side of channel they have enough capacity. If I use channels with larger capacity, they are I will increase my chance to forward money. And if I have lower hubs, right? If I have, let's say I want to pay Y, if I pick this pass, it will be cheaper probably it will be cheaper compared to picking this pass or this pass. So I have these criteria to find my pass. And there are a couple of algorithms that allow you to do this. The first and obvious one is trial and error. And because, as I said, these payments, they are atomic. So either your payments will be successful or they all will fail, right? So in this example, first I pick this pass, and if it fails, if it at this node says, I don't want to move your money, or I don't want to forward your money, or I don't have capacity, then I will pick another pass. And I will do this again and again uh, until my payment is successful. The next idea is I can break my payment, right? If I want to uh, if I want to pay a large amount of money to increase my chance, because all of these payments, they are atomic, right? If you remember, you need to know a pre-image, so you can get your money, right? So I can create as many as I want. And at the end, if everything is successful, then I will give the pre-image for the money. So here he says, okay, first I will break in the first round, I will break my total amount into 26 parts, and I can move these parts. And then again, for this, the other 6 parts, again, I will break them. So I can move them until I can move all of my money. This is, of course, you will increase your chance, but you have to pay more transaction fee because you are using more routes. So basically, the idea here, I have a very big network, and if I want to pay someone in the network, I need to find my pass. And because of the network setting, the fact that I don't know the balances, you can have different strategies or heuristics to forward your payment in the network. And in security and privacy, this is the last part. Security and privacy for the Lightning Network. Usually, we care about 3 concepts. We care about confidentiality, integrity, and availability. So in Lightning Network, we mostly care about availability and confidentiality. And we care about the fact that only sender and receiver, they know the payments, and no one can leak link sender and receiver together. But even though they had these ideas and they were designing, there are some attacks that you can basically de-anonymize people in the Lightning Network. And let's review these attacks very fast. The first attack, they call it probing, which I want to know how many balances, which I want to know the balance distributions. And how I can do this, I just create a lot of random payments, and I ask people to forward my money. And if they forwarded my money, I will know. I will have an idea. I will have a guess that what is the balances, right? Because they at least they can forward my money. They can forward my the amount that I ask, and I will increase it eventually. And at the end, I never publish the pre-image of the hash, so everything will be reverted. So, and I will lose nothing. But in the meantime, if I do this a lot, then I will find about channel balances. And usually every protocol, you can always do denial of service attack. And basically it means that you can jam the network. You can create a lot of stupid payments without releasing pre-image, right? And just force the network to wait for you. And even though at the end they all will be timeout, you're still jamming the network. And of course, the last attack is linking senders and receivers, because at the moment, the Lightning Network, it looks like a star, the graph. And here in 2022, because the network is something like this, instead of something like this. This guy can observe a lot of payments, right? And in this middle guy. And in 2022, one guy could see half of the transactions, or the foremost central nodes could see 72%. So even though the idea of they try to make these payments confident. There are still some problems with the network that we can solve. But to conclude my session, the Lightning Network is even right now it's a very people use it more commonly. The total capacity this is for mid 2021. Now it's more. The total capacity is 200 Bitcoin, which is a lot. And people they have started using these layer 2 protocols, or we call them layer 2 or off-chain protocols a lot more because they are a lot faster, they are cheaper, and as a result, right now they are very successful. And honestly, a good percentage of researchers, the blockchain, they are either usually proposing new layer 2 protocols, or they are trying to solve the current problems, right? For example, the one that I explained here, finding a path in the Lightning Network it's harder than usual. And that's it. Sorry if it was a little bit rushed. I can provide some links, or I can always answer some questions. But if you have any question right now, I would be happy to answer them.